And before I get into it, there's going to be a lot of math and derivatives and integrals and stuff like that, and it's easy to get lost in all that. So I just want to kind of point out what we're trying to talk about. Let's pretend like we have an injector and a producer. So we've got, this is an injector, I'll put I, and this is a producer P. And if you inject it over here, and then it flows over to the producer well, and some of the flow is going to go straight, okay, and the shortest distance between 2 points is a line, but some of the flow might go like this, some of the flow might go like this, some of it might go like this, some of it might go like this, okay? So it's traveling along those paths, right? And there's actually an infinite number in between there, but we'll just draw a few. And so some of the water that you inject is going to go along this, what we're going to call a streamline or a path line. They are different in unsteady state flow, but our purpose is, if we're looking at steady state flow, path lines and streamlines are the same, but some of the water might go over here, and it might take longer to get to the producer well. And some of the things that we're interested in is understanding what these streamlines or path lines look like. So we want to make plots of those. We want to know what the pressure field or the potential field, so let me just draw this out. I'll say we want to know the streamlines or path lines for flow. We want to know the pressure or potential field, and we remember that potential is just sort of a pressure corrected by gravity. So in the absence of gravity, pressure and potential are the same thing. I'll keep it general and use potential, but if it helps you, you can replace potential with pressure, because in the absence of gravity, they're the same thing. And we know the derivative of pressure or potential with space, and you multiply that by permeability divided by viscosity, you get the velocity field. So we also want to know the velocity, Vx and Vy field, right? And so maybe I'll call this the x direction, I'll call this the y direction. And so, you know, especially if you're on one of these, this is going to have an x and a y component of velocity. Okay, and maybe not surprising to you, but the velocity near the wells is going to be much higher than far away from the wells. Right? You're going to have a high velocity near the wells, and that's due to the radial flow. The analogy I like to give is, you fill up your bathtub and you open the drain at the bottom and you look at the water flowing, the velocity is clearly very fast near the drain, and it's very slow far away from the drain. And so the velocity is a function of distance. So it's going to be higher near the wells and slower far away from the wells. But those are some of the things that we're going to be doing. So we're going to use Vx and Vy for velocity. We'll use this for potential, so this phi term. And for streamlines, we're going to use a weird variable. It's going to be this psi term. Okay, so that's some of the variables that you'll see. So how are we going to derive some of these equations? Well, we'll start out with some really basic stuff that we know, like Darcy's law. So we know that Darcy's law in radial flow, and why radial flow? Because right around the wellbore we're in radial flow. So we know that the velocity in the r direction is given by minus k, the permeability, divided by the viscosity, times the partial of potential with respect to radius. Now again, I use potential because you could have gravitational effects there, but if there was none, then you could just substitute this phi with p for pressure. So if it helps, think, when I show potential, just think pressure. And also, this is the velocity, right, like feet per day, but if I want to know the flow rate around the well, QW, it's the velocity times the cross-sectional area, or the area of flow. And the area is going to be 2 pi RH. So what I get is minus k over mu times the area is 2 pi RH times d phi dr, right? So 2 pi RH, let me just grab something here. So this is kind of from a basic geometry class, right? So if we want to know the surface area, this is my well bore, I want to know my surface area, then it's 2 pi r times the thickness h. So it's 2 pi RH. So this is QW. That's the flow rate, like barrels per day, around the well. That could be an injector or a producer. Now, if we want to know potential, what you can do is you can integrate. All right, so I'm just going to move things around. Let's say I have a constant rate well. Let's say I'm injecting at constant rate. Maybe if it's steady state, then I'm also producing at constant rate. And what I can do is I can do D potential, right? I'm just going to separate my variables, is equal to, pull out my constants, mu Q to the well divided by K 2 pi H times the integral 1 over R dr. Okay, so this integral is obviously very easy. These are all constants, and this is the integral of 1 over R dr, which is just the ln of R. So if I solve this, I get the potential, or again, pressure in the absence of gravity, is a function of radius, and it's going to be equal to minus Q, I think I dropped a negative sign somewhere in there, so it'll be a negative there, so minus QW, viscosity, 2 pi kh times the ln of R plus, well, we need some constant of integration. Okay, so if we really wanted to know the potential or the pressure at any given location, you're going to need some sort of boundary condition, right? So if you want to know the pressure at some distance away from the well, maybe you need to know what the pressure is at the well, right? So we have this constant of integration, so we don't completely know what that is, but we do know that it's a function of radius and it's ln of radius. And that sort of makes sense, that the pressure is going to change a lot when r is small, but as you go further out, it doesn't change as much, right? Because we know if you were to plot, you know, the ln of r versus r, you get something like that, right? And it just sort of slows down as you get further away. Okay, so this is our solution. This is the potential, or the pressure, as a function of radius. We don't know C, but maybe we don't need to know it, or if we did know a pressure or potential at a different R, then we could compute it for all R's, because then we'd have our boundary condition. Now, one thing I want to do is I want to convert this equation to put it in terms of X and Y, because, you know, I have a cylindrical well bore, and I'm flowing, you know, when I inject around the well, so I can use Darcy's law, but maybe I want to know this, the velocities and potentials as a function of X and Y. So I need to convert radius to X and Y, and this is sort of an old trick from your geometry or trigonometry class. We know that X is equal to R cosine theta, and Y is equal to R sine theta, and we know that X squared plus Y squared is equal to R squared. What that means is that R is equal to the square root of X squared plus Y squared. Right? That's just basic trigonometry, right? And so what I can do with that is anywhere I see my R, which is like right here, I can replace it in terms of X and Y. So then I can write my equation for potential in terms of X and Y. So I can say, therefore, phi of X and Y is equal to minus QW, viscosity, Okay, now you might notice that I had a 4 here, and before I had a 2. That might look odd to you. The reason is that this was supposed to be the ln of the square root of x squared plus y squared, because that's what r is equal to. Or another way of thinking square root is x squared plus y squared all to the 1/2 power. And if you remember your rules of logarithms, if you got a exponent over there, you can pull it down below. So you had 2 times 2 is equal to 4, and you lose that exponent. So that's just a rule of logarithms. Okay, so that is the potential. And that would be if your well is at a location 0, 0. If you had a well, if the well is located at x is equal to xw and y is equal to yw, then your equation is offset. So what you have is phi of x and y equal to minus qw 4 pi kh times the ln. Now it's x minus xw squared plus y minus yw squared. And the constant of integration might be different. I'll call it C2, but right now, it doesn't matter. To know the exact potential, we would need a boundary condition. Okay, sometimes we don't need to know the exact potential. Maybe we just want a difference in potentials. Or we want to take the derivative of potential with distance to get velocity, in which case that constant of integration will go away. So I'm not going to worry about that too much right now, but this gives us an indication of how the potential or pressure varies with space, x and y, and it's given by this equation. Okay, so now that we have that, this would be for one single well. Okay, but we probably don't have one well. We probably at least have 2 wells. We have an injector and a producer well, but we might have more than that. Okay, all the time in a reservoir we'll have multiple injectors and multiple producers, and it probably doesn't surprise you that their solutions interact with each other. And maybe I'll try to give an analogy, but if you threw a rock into water, then you'd see these waves come out, right? And so these waves would spread out, spread out, spread out. And likewise, those would be like pressure pulses. But what if you threw 2 rocks and you threw them close to each other? Well, maybe at early times they'd be spreading out and they wouldn't interfere, but eventually those pressure pulses would come and start to interfere with each other, and those waves would interfere with each other, right? So it's the same thing. So if we have multiple wells, then we need to add these solutions on top of each other. So we need to use the principle of superposition. And in reservoir engineering, you've seen this. I think this is the 4th time you've seen it. You should have seen it in Reservoir 1 when we talked about well law, when we talked about well testing, okay? And you talked about these solutions like a step rate test, where you had you're changing the rate, or a well shut-in test. So you learned about superposition there. Then we learned about superposition again when we were talking about aquifers earlier this semester. We learned about superposition when we were looking at the solution for a tracer when we just injected it for a period of time. Okay, and what we've learned over and over again is that there's some mathematical problems, specifically they're linear problems, and we won't get into the details about that, where if you've got multiple responses to something, like if you have multiple wells, then you can just directly add the solutions together. Now, I will say there are some physics and some math problems where you can't just add those together. They are not considered linear, and the principle of superposition doesn't apply. The key thing for us here is that it does apply, and that's really all you need to know. Okay, and so what you can do is you can add those solutions. So imagine you had a reservoir, and this is again X, and this is Y, and you had wells, right? And so you had, this is X1, Y1, and this is X2, Y2, and this is X3, Y3. And each of these had some sort of potential as a function of X and Y. Okay, it increases, it changes as you go out. These pulses getting larger, they start to interfere with each other. And if you wanted to know what the potential is at some place, some random XY in your reservoir, and it was at a place to where these started to interfere with each other, then you would need to add your solutions together. So if you have multiple wells, then your equation looks like potential is a function of X and Y. It's again minus mu over 4 pi kh times the sum of all my wells, I'll call it NW or N, QI, well, L or I, so QI times the ln of X minus XI squared plus Y minus YI squared plus some constant of integration. Okay, doesn't matter what I call it. I think I called the last one C2. I can call this C3 or just leave it as C. It doesn't really matter. The point is it's a constant of integration. So let me comment a few things about this. Is that we have multiple wells. So I said from I is equal to 1 to N or N wells. Could be 2 wells, could be 10 wells, could be 100 wells. And each of those wells have a different location Xi and Yi. Xi and Yi. And then each of the wells could have a different rate, Qi. Okay, one rate could be injecting at 500 barrels per day, and the other one could be injecting at 1,000 barrels per day. Another well could be a producer well, in which case they would have an opposite sign. I did assume in this problem that the permeability, the thickness, and the viscosity are uniform and homogeneous. That may not be true, okay, but really we're trying to come up with solutions to help us to understand this aerial displacement efficiency. So this is the solution for multiple wells. Okay, so if you had a boundary condition, if you knew the potential in any location, and maybe you know what it is at least one well, you have a pressure gauge or something in there, and you get your constant of integration, and then you could find your potential at any other location in the reservoir, at any X and any Y, provided you knew your well locations and your injection rate, and of course you know the permeability and viscosity and thickness. The C2 is determined, or any of these constants of integration, I'll just talk about the last one because that's what I finished with, is determined by the pressure at some known location. So it's just a boundary condition. So if you know the pressure at one well, okay, or one location, then you could plug that into your X and Y, solve for your potential there. That would give you C3, and then you knew your potential everywhere. So the whole point is that you can't determine potential in general unless you know that potential or pressure at one place. So there's lots of cases, obviously, where we have multiple wells and they're interacting with each other. There's one specific case where we have to do that, and that is when we're near a fault or some sort of seal. Okay, so if we're like at the edge of a reservoir. So imagine I've got a well, and there is a fault here, right? So there's no flow at this boundary. Well, you can imagine that if you were to inject fluid, you would start, fluid would start coming out radially, right? And it could go, it keeps on going out. But what does it do in this direction? It wants to go this direction, but then it's got to turn up, and it's got to go over here, and it's got to turn down, right? Okay, so you had radial flow over here. So if you didn't have this fault, it would be super simple. You could just use basically this solution over here. You have one well. You don't have to use principal superposition because you've only got one well. And this gives you the solution for potential, and we'll learn later how we determine the velocity field and what these streamlines look like. But if you did have this seal or fault, then you can automatically see that something weird happens at this distance. And I'm going to call this a distance L away from the well. Okay, so as it approaches this, the fluid can't go through the wall, through the seal. It's got to kind of avoid up and turn away from it, right? So something weird happens over here. Now, how do we describe that mathematically? How do we model that? Well, it can be a little tricky, okay? You've got this boundary over here that's going to make the math complicated. We're going to come up with sort of a mathematical trick. We're going to come up with a mathematical trick that doesn't include a fault, but instead tricks it into something that's mathematically the same. And to do that, we're going to create, I'm going to call this a real well. And on the other side, exactly L away, there's going to be another well that's a fake well. We're going to call it an image well. Okay, so this is a real well. And this is a different well, it's an image well. And what I mean by image well, it's almost like this well is looking at itself in the mirror. My seal is like a mirror, and on the other side, it sees exactly the same thing. It's its opposite, right? It's its image. And so we can pretend like this seal is gone, and you have one well over here and one well over here. Now they're both injectors, they're both producers. Okay, this is not an injector going into a producer. This is two things that are identical. So if you're injecting 100 barrels per day in the real well, then we're going to inject 100 barrels per day in the image well. And what happens is that those two wells, the real well and the image well, interact with each other, and they affect each other's streamlines. So over here, flow is going to go like this, right? But as you go over here, it's going to turn up as well, right? Because this is affected by this streamline. So when you have two streamlines coming at each other, they're going to turn and go away from each other. Okay? So what that means is that we can mathematically describe flow around this well in the X and Y coordinate system when we have a fault by tricking it into just saying that there's an image well on the other side of the fault that interacts with it. And fortunately, we have a solution for that. We use superposition, and we now know how to describe the potential when you have more than one well at in more than one location. Okay, in this case, I said that the rates could be different. In this case, for the real well and the image well, they'll be exactly the same. The positions, well, the Y positions will be the same, but the X positions will be opposite of each other, right? So this will be maybe negative L and positive L away, depending on what I call my origin, if this is my origin right here at the fault. So what my mathematical solution looks like, this is for a single well, a single real well, but near some sort of barrier. Okay, so that's my solution. Hopefully you can read that okay. It just came from that solution I had previously for multiple wells with the principle of superposition. I only had 2 wells, so I didn't have to write the summation. I just wrote the 2 terms. You know, everything is the same. It's symmetric. It's this image. So the viscosity, permeability, and thickness are going to be the same in both cases. The well rate is going to be the same in both cases. If I wanted to, you know, I could have pulled this out of this bracket here because Q1 and Q1 are the same. Remember, this is a mirror image of each other. So if I'm injecting 100 barrels per day in the real well, I'm injecting 100 barrels per day in the image well. The Y location is the same in both cases. So Y is equal to Y1 and Y is equal to Y1 for both the real well and the image well. However, one thing that is different is that in the real well, we were at negative x1. So x minus negative x1 is x plus x1. But on the image well, x was equal to positive x1. So x minus positive x1 is x minus x1. Okay, and there would be a constant of integration again over there. But this would give us an idea of what our potential field is for one real well, but near a fault. But again, we're not really modeling the fault. We're tricking it into saying that there is a mirror image of that well on the other side of the fault that interferes with our original well. And that's the solution we get. Now, what I will say is that we could have multiple faults or multiple wells. And they could be they could be on the right, the left, the top, and the bottom, in which case you had mirror image wells on all sides, right? So not just on the right, but on the left, on the top, the bottom. Okay, and you could do something like that. So let's talk about velocity fields now. Remember I said we're going to look at potential or pressure fields. We're going to look at velocity fields. That's like ux and uy. And then later we'll look at these path lines or streamlines. So the velocity is given by Darcy's law. So the velocity at any point, ux at some point, I'll call it xj, yj, is given as minus k over u partial phi with respect to x. All right, this is just Darcy's law. Maybe you're used to seeing pressure instead of potential there. I put x there because the velocity can have an x and y component, right? Now, you know, up until I guess today or Friday, we were always talking about things in one dimension. So I didn't really worry about x or y, but now we're in 2 dimensions, at least. We'll go to 3 dimensions later. So velocity has an x and a y component. And the x component is the derivative of potential or pressure with respect to x. And the y component is respect to y, okay? And in both of these cases, I might want to know it at a very specific location, xj, yj, again, xj, yj, because potential, we just learned, is a function of x and y. So the derivative of potential, and therefore the velocities, are going to be a function of x and y. Okay, so they'll vary with x and y, but we might want to evaluate that velocity at a very specific location. Maybe that specific location is at the wellbore, but we might want to do it at other locations as well. Okay, so let's we're going to need that. We're going to need that, and we'll go back to the very general case where we had we use superposition. We have multiple wells. Okay, if there's only one well, then that summation just is 1. We don't have to worry about it. If it's an image well, then that's okay. Then you've got just 2 different wells that are equivalent, but the most general case has got this summation there. And what we need to do is we need to take the derivative of this equation with respect to x. Okay, that looks complicated, but I mean, this is a constant. Qi is a constant. And really what you need to do is you need to take the derivative of ln, which isn't so bad. And so then I can say that u of x is equal to minus k over mu times, you're going to have that coefficient, that mu over 4 pi kh. This is a 2. Okay. Now let's go back. Let's look at this. This was my potential, right? I wanted to take the derivative. So I get my mu over 4 pi kh and q. That doesn't go away. That's why it's mu over 4 pi kh and q. Then I got to take the derivative of this thing, this ln of x minus xi squared. So that's a little complicated, but we know that that what you do is the derivative of ln of something, the ln of z is 1 over z, so that's why you get the x minus xi squared plus y minus yi squared. But then you got to take the derivative of the inside, so it's 2 times x minus xi. So it's a pretty straightforward derivative. And so this gives you the velocity. And if you notice, then there's no constant of integration anymore, right? Because you take the derivative of a constant, you get 0. So this is the velocity. And I could simplify this a few different ways. So I could simplify this by canceling my velocities, canceling my k's. Okay. You could do the same thing for the velocity of y. So I can rewrite this as, I can say the velocity in the x direction is 1 over 2 pi h times the sum this is at a specific location j, so xj, yj. So xj minus xi squared plus yj minus yi squared. Let me make a few comments about this equation. So xi, yi is the location of the well, or the location of each of the I wells. There could be more than one. QI is the production rate, the constant production or the constant injection rate of that well at I. XJ, is the position at which I'm interested in calculating the velocity. So I'm trying to find this at XJ. The other thing I'd like to point out here is that permeability and viscosity don't show up into that equation. So if I have these wells and I have constant rates, constant injection rates, constant production rates, then the velocity field is independent of permeability and viscosity, at least if they're homogeneous. So having a more permeable medium won't change the velocity at all for a constant rate. It'll change the pressure, but it won't change the velocity. Likewise, I could write for Uy, it's equal to 1 over 2 pi h, sum from I is equal to 1 to n, Qi times Yj minus Yi over Xj minus Xi squared plus Yj minus Yi squared. So you have an X and a Y component of your velocity. If I go back to the very first page when I was drawing, is that if fluids are flowing in one direction, okay, flowing from over here to over here, the velocity has both an X and a Y component. It can be flowing in the X direction, it's got the Y direction, and sometimes we talk about the magnitude of the velocity. The magnitude, U, is the square root of X squared plus Y squared. So let's say Ux was 1 foot per day, and Uy was 2 feet per day. Okay, then U would be the square root of 1 squared plus 2 squared, which is the square root of 5, okay, which is a little bit greater than 2. We might also talk about the angle theta, which is the inverse tangent of the y and x velocity. That theta is an angle, right? These are vectors, the x velocity and the y velocity, and you have vectors. Let's see what we have here with. Okay, so I'm going to take a step back because there was a question about these image wells. Okay, somewhat arbitrary where you place this, but the way I did it is I said that this is x is equal to 0, right where the fault is. Okay, and if we wanted, we could say, well, let's just say that this is right over here, y is equal to 0. Okay, it's again arbitrary, but let's say we've done it over there. Well, in this case, this position is some minus xi, and I guess if I'm calling this L, it's minus L away, and this is a plus L away, or a minus xj and a plus xj. Okay, so, but again, it's somewhat arbitrary. You can draw your coordinate system however you want. I've made this fault x is equal to 0, so this is some negative x, and this is some positive x. And because of that, when I made my equation, and you sum these two wells together, the real well and the image well, this is an x minus a negative x1, or L, either one. And so a negative times a negative is a positive, and then you get an x minus positive x1, so you get x minus x1 squared. So you all have a wonderful day.